In two dimension, we knew that if we take the derivative of a function, that is going to give us the slope of the tangent line. So here, my df by dx will tell us the slope of the tangent line, Now, in higher dimension, my graph is going to be in 3D now. So the graph of my function could be like a 3D function. So this is like a 3D thing, by the way. Now then, what is going to happen here is the partial derivative df by dx and df by dy. It is actually going to tell us the slope of the tangent. But it's not going to be a tangent line anymore. The thing that is tangent to my graph here is actually going to be a tangent plane. So let's take a look at the next example that we have here. My function is x cubed plus y squared minus xy, and I would like to find an equation of the plane that is tangent to the graph of this function at 1, 1, 1. So notice how 1, 1, 1 here. What this means is my x is equal to 1, my y is equal to 1, and my z, which is f of x of y. Notice how if I plug in x equal to 1 and y equal to 1, I'm going to get 1 plus 1 minus 1, which is going to equal to 1. So that's what these three numbers mean. So now let me actually just go ahead and take a look at what the graph of this function look like. So I have here the green thing. This is my x cubed plus y squared minus xy. So this is the graph. This is indeed the graph of the function that we are looking at earlier. And the blue point on the graph here, you can kind of spot this little blue point, its coordinate is 1, 1, 1. So now let me just show you the tangent plane that is tangent to this green graph at the blue point. So I'm gonna get this blue plane here. So you can kind of notice how the blue plane indeed is tangent to the graph at exactly the blue point. So let me try to find the right angle. So maybe about here. So you can kind of see that indeed this guy is tangent to the green curve. And we actually kind of see that the equation for my green line, for my blue line, blue plane, is negative 2 plus 2x plus y. So how could we find the equation for this thing? So let me kind of go back at the problem here. So now if we take a closer look, let's say I have the 3D function here. And my green graph looks something kind of like this. And I have the point of 1, 1, 1 here. And I'm looking at the blue plane that is tangent to this green graph at exactly that point. Well, what properties does this blue plane have to have? Well, one thing for sure, because it is tangent to the green curve, right? So it has to have the same slope. It has to have the same slope. It has to have the same slope, and it also has to passes through the point 1, 1, 1. So if I can find an equation of the plane that has these two properties, then that should indeed be the tangent plane to my function. So now let's talk about the first one. This guy has to have the same slope. And whenever we are talking about slope, that means we are talking about the derivative. So it seems like I'm gonna first have to find the derivative of this guy. So let me go ahead and find the derivative of this guy with respect to x. So my f sub x, let me see, is going to be, so let me just go ahead and take the derivative. It's going to be 3x squared. And because y, I'm going to treat it as just a number. So the second term would just be 0. And the last term, negative xy. Again, the derivative of x is going to be 1. So this is just negative 1 times y. So this is what I'm going to get. And I would like to find the tangent plane at the point 1, 1, 1. So the value of my x and y is going to be 1 and 1. So I'm going to evaluate this thing at the point 1, 1. And what I'm gonna get is, let me see, 3 times 1 squared minus 1 times 1, and I'm going to get 2. Okay, so now I find f of f sub x. Let's do it again for the f sub y, which is the derivative with respect to y. If I find the derivative of this guy with respect to y, the first term x cubed would just become 0, y squared, its derivative would be 2y, and the last one, the derivative of negative xy would be just negative x times derivative of y, which is 1. And then again, if I evaluate this derivative at the point 1, 1, what I'm gonna get is, let me see, 0 plus 2 minus 1, and that is going to equal to 1. So I find the derivative with respect to x, and that equals to 2, and I find the derivative with respect to y, and that is equal to 1. So if we stop and think for a moment, we would like to find an equation of the plane, and we knew that the general form for the equation of a plane would just be ax plus by plus cc equal to something, let's call it d. So I would like this plane to have the same slope as these two values. So what I can do is, I can manipulate this equation a little bit. I'm going to move ax and by to the other side. So I'm gonna divide both sides by c. So I'm gonna have that my z is gonna equal to, well, let me kind of move this two things to the other side first. I'm gonna have cc is d minus ax minus by, and I divide both sides by c. So I'm gonna get that my z is gonna equal to d over c minus a over c minus b over c. And so here is my equation for the same plane. Now I can actually find the slope for this plane as well by by finding the derivative with respect to x and y. So given this equation, I can find the partial derivative with respect to x, let me use dz by dx. My dz by dx is just going to be here. X is my only variable, so d over c is just a constant, so it becomes 0, minus a over cx. So the derivative of that is just going to be a over c. And then minus b over cy, here is just one big number, so it's just a constant, so the derivative would just be minus 0. So I'm only left with negative 1 over c, and this is my partial derivative with respect to x. And how about my partial derivative with respect to y? If I find dz over dy, I'm gonna get, let me see, this guy would just be 0, minus, there is no y here, this is just one big number, so it's just 0. And the derivative for the last term would just be minus b over c times 1, so it's just negative b over c. So here, the derivative dz by dy would just be negative b over c. And what do we know? Well, we would like the slope dc by dx, this thing, to match the slope of the curve that we have to begin with. So I would like to have negative a over c here to equal to 2. So this guy should equal to 2. So negative a over c, this should equal to 2. And I would like to have my dz over dy, which is negative b over c here, to equal to the derivative, the same slope with respect to y, which is going to equal to 1 here. So actually, let me change the color. Let me do it pink here. Okay, so I would like to have negative b over c here to have the same slope with respect to y. So I would like to have this term equal to 1. So then, if I look back at my equation, it seems like I'm gonna need negative a over c, this guy, the yellow term, has to equal to 2. And this guy, negative b over c, this pink guy, has to equal to 1. So now the equation of my plane becomes, let me see, c equals to d over c plus 2x and then plus y. Notice how, because negative a over c, the whole thing is equal to 2, so this is just d over c plus 2x and then plus 1y. Now then, well, it seems like I only need to find this value for of d and over c, and I'm going to be done with the problem. And there is just one information that I haven't used yet, which is the fact that my planes has to pass through the point 1, 1, 1. So what that means is I can just plug in x, y, and z to all equals to 1. So what I'm going to get is my 1 is d over c plus 2 plus 1. So then the value for my d over c has to equal to negative 2. So d over c has to equal to negative 2. So if I plug this back into my equation, what I'm going to get is that the equation for my plane is going to be z equal to negative 2 plus 2x plus y plus 2x plus y. And indeed, this is the equation of the plane that we have looked at earlier, negative 2 plus 2x plus y. So here is how we can find the equation of the tangent plane for the 3D function. But before we finish, let me also mention something real quick. Notice how the coefficient of x and y here, 2 and 1, this 2 thing, well, it actually turns out just to be the derivative f sub x and f sub y. So it's just the partial derivative with respect to x and with respect to y that we have seen earlier. So in general, let me kind of write somewhere. So maybe you can write that here. Let's say if I want to find the equation of the tangent plane at the point Q, the general form for this plane is going to be that my z is going to equal to something plus something x plus something y. And this something is going to be the partial derivative f with respect to x. So let me actually just write dz by dx. So it's the same thing anyway. So let me just write the f of x is fine. So it's just going to be f sub x when at the point q. And this other term here, this is going to be the derivative of f with respect to y at the point q. So here is how we can find this constant by just plugging in the value at the point of tangency, like what we did here. So here is how we can find the equation for the tangent plane.